functional solution to an integrable deformation for commutative the algebra of skew hermitian ZhZ-matrices.
First, let me start by thanking the organizers for inviting me to come. It's always a pleasure to come to Moscow. So this is a joint family work, as you can see. That's okay, the plan of my talk is as follows. I will discuss an integrable hierarchy. You need, first of all, some arena where the deformation takes place. And that's, in my case, is the pseudo-difference operators. In the pseudo-difference operators, you also need relevant decomposition in the direction of two Lie algebras. Then you will take in one component of the decomposition, you take the commutative algebra, and then you use the group from the other component to deform the commutative algebra you started with, and the deformed generators of this commutative algebra then have to satisfy a set of Blacksky equations. This is no, it's over. Okay, and this deformation of this commutative algebra will be named after the commutative algebra that gets deformed. Now, there are a few handy relations, the zero curvature relations that hold, and they are a starting point for the construction. Make the solutions uses the technology of the linearization and wave matrices. What you construct is a module of the pseudo difference operators. Then you look for special vectors in this model, and these special vectors are the wave matrices. And those wave matrices should satisfy a set of equations, and that you call the linearization. And you can easily see from those equations that you get in this way solution. And the geometry will come in the last part, that I will construct a complete set of operators that generate solutions of this. So I will start with discussing the coefficients of the pseudo-difference operators, real valued functions, RR, and look at complexification. Then I skip the tensor product and simply write alpha F for this complexified vectors. Now you can introduce complex conjugation on the algebra R, and you do that on the complex component of this tensor product. You can also speak of positive functions. That those are all functions that have in every point a positive value. Now, the pseudo-difference operators are a part of the ZhZ matrices with coefficients from R. And as usual, we define the transpose simply by flipping the indices of the matrix. And if you add complex conjugation, then you get the accurate. Now, the pseudo difference operators I completely express in two types of matrices. The first matrices are the diagonal matrices, and I call this algebra D1R. There is an embedding of the coefficient ring into D1R by taking all coefficients on the diagonal equal to R. Now, the second part operators that you use is the shift matrix lambda. It acts on the diagonal matrices by shifting. That's number one. And like this, you can decompose any ZhZ matrix in diagonals. And the ith diagonal is lambda to the power I times diagonal matrix, and that is element diagonal elements as S plus I. Now we look at all elements in the ZhZ matrices that have only a finite number of positive diagonals, and that's the pseudo difference operators. Now you easily see that this is an algebra, and if you have an element in this algebra with a leading diagonal coefficient that is invertible, then this element is invertible. So you have a ton of operators that are invertible. Using this property, you can see lambda minus the identity is such an operator that's invertible, and that's a difference operator. Now, then you can also express all the pseudo difference operators as a sum of a diagonal matrix times delta to the power I, and delta to the power I is the i's power of the difference operator. And this explains the name of pseudo difference operators. Now, I start with decomposition of the pseudo difference operators. I take SHR are the skew hermitian matrices in the pseudo difference operators. So A star should be equal to minus A. Now you can easily see that the general element has this form, with the zeros diagonal being completely imaginary, and all the other diagonals are arbitrary. Now, this SHR has a complement inside the pseudo difference operators. That's the P minus R. It consists of all pseudo difference operators that have zeros diagonal. That's real, and all other negative diagonals are arbitrary. And the intersection of those two the algebras is zero by construction. So we have in the direct sum, and yeah, you can express easily the component the component in each of the two Lie algebras. And the projections I denote by P minus and by P SH. Now, we can associate a group to the first Lie algebra, P minus R. If you take the exponential mapping of an element in P minus R, and if it is well defined, then you get you see this calligraphic P minus R as the group associated with the Lie algebra P minus R, and you use this group to deform a commutative Lie algebra in the skew hermitian matrices with coefficients over C. There is a real analog. Instead of taking skew hermitian, you work in a real setting. So you start with a commutative algebra of real valued function. I denote it as R anti-symmetric. For the elements are now, instead of A star is minus A, it is simply the transpose of A is minus A. You can easily express elements of this form in a finite number of powers of lambda. Here we have again a complement. I call this complement P smaller or equal than 0, and it consists of that of all pseudo difference operators that are of order 0 or lower, and all coefficients are in the ring R AS. This is again a complement. We get also in the real case, we get a splitting, and the projections I denote in the same way, like the algebra say correspond to this P smaller or equal than 0 or P AS. Now, we can again consider a group. With respect to this first Lie algebra, it consists of all operators of order 0, such that zero's diagonal is invertible and positive. And that's again the group that we use on to deform the commutative Lie algebra and ASR. Now, what are the commutative algebras I'm going to use? I take first the Lie subalgebra CSHC, spanned by the elements are written here, lambda j, the j minus lambda to the power minus j. Those are the matrices with real coefficients, and G02 and J2 are the matrices with imaginary components. Now, it's easy when we make a notation for the index set of this basis. And the first set of indices I denote by sigma 1, and the second set is for the imaginary ones, the sigma 2. So sigma is the total index set. And it's easy to show that this algebra is maximal commutative in the skew hermitian matrices over C. So this algebra is optimal as for commutativity. Yeah, you will not forget any direction that is there. And the G sigma are called the basic directions of this linear algebra. And it is algebra ZhZ is deformed by the group polygraphic P minus R. Now, I will speak of P minus R. Deformation of the G sigma is a collection of matrices that are obtained by conjugating is an element G from this polygraphic P minus R. And this G we call the dressing operator of the element G02 remains the same because that's I times the identity. But for completeness, I included it. Now, what are the evolution equations? Get evolution equations, we need that the algebra RR, so that's the real part of the complexification R has a set of R linear commutative derivations partial sigma. And partial sigma is an algebraic substitute for differentiation with the flow with respect to the flow parameter corresponding to this real algebra G sigma. Now, all this partial sigma we extend to C-linear derivations of this bigger ring R by simply this definition. And you can let partial sigma act on the matrix coefficient of each pseudo difference operator, and you get a C-linear derivation of this algebra. And what are the evolution equations? Now that's are written down here. So you get the derivative with respect to partial sigma 1 of polygraphic G sigma 2 is equal to the projection corresponding to the projection of G sigma 1 on the second component, and then the commutator is G sigma 2. And because all elements of G sigma commute, you get the last equality for free. Now, and we call the data R this set of derivations, a setting in which we can consider the deformations. Now we look for polygraphic P minus R deformations of the G sigma that satisfy the equations 4. And if you have found such a deformation, then you can call that a solution in the setting we just introduced. And the Lux equations that have to be satisfied by this deformed generators are the Lex equations of the ZhZ hierarchy. And there's always a trivial solution, simply not correlating with the identity. Yeah. Now, we have the same in the case of the real algebra. Then we only have after the matrices that we have before, or we miss all the imaginary matrices. And script J is the index set of this basis. And that's also a maximal commutative reason algebra of the anti-symmetric matrices, this coefficient from R. And again, we call this basic elements the basic directions of the real algebra. And we are going to deform the Fj with the group calligraphic P smaller or equal than 0. Now, then we have the notion of a P calligraphic P smaller than or equal to 0 deformation of the Fj is simply a collection of matrices that are obtained by conjugating with an element of this group. And we define the evolution equations of this deformation in Formula 5, and that's the analog of what we saw for the complex case. Now, also here you have always a trivial solution, and we name the hierarchy after the commutative algebra that gets deformed. Now, what can you show? These deformed generators not only satisfy the Lex equations, but if you look at the projections, P sigma, so the projections on this skew hermitian matrices of the deformed G sigma, then they satisfy with respect to these projections the zero curvature equations. And the same holds if you take in the real case the projection on the anti-symmetric part of the idea. Now, those zero curvature related are in fact the compatibility conditions for the Cauchy problem that we will see in a moment. Besides the B sigma, if you take A sigma is B sigma minus calligraphic G sigma, then the A sigma satisfy also a zero curvature equation. And the same for the real case for the dj is cj minus fj. And you see the zero curvature equations down there. Now, there are these equations satisfy also an analog of the Sato-Wilson equations for of KP hierarchy. For the suppose we have such a set of deformations. This is the complex case. The real case is on the next sheet, for it did not fit anymore. So if you take you have the A sigma as defined in number 6. So that is B sigma minus calligraphic G sigma. Now, then if the dressing operator satisfies the equations partial sigma k is A sigma times k, that's a Cauchy problem. Given A sigma, then you can try to solve that for an operator k that belongs to the group P minus R. Now, if it satisfies this condition, the zero curvature equations for A sigma says that it is a good problem to consider, but that's necessary. Now, so if the K, if the dressing operator satisfies this, then it's automatically a solution of the CSHC hierarchy. And this equation 7 are called the Sato-Wilson equations. That's simply in analogy for the KP. Now, we have the same also Cauchy problem, but now with the operators DJ. And if the dressing operator satisfies this Cauchy problem 8, then automatically the FJ are a solution of the real hierarchy. And also here we use the term. So this proposition gives you an idea of how to construct solutions of this hierarchy. You have to find dressing matrices that satisfy the equation 7 or 8. And that we are going to do in this special so the difference model. We look for special vectors, the wave matrices, that satisfy the linearization of the hierarchy that we consider, and that will be come here. Yeah, so I start with the deformation of both the G sigma and of the FJ. Now I will first show the equations you have to satisfy, and then later I give the formula. We have the following equations. We have G sigma acting on phi is phi times G sigma, and the partial sigma of phi is the projection of G sigma times phi. Now, this is called linearization, and if you do a set of manipulations, we differentiate the first equation with respect to sigma 1, and then we substitute twice number 10. So it's written out here, and what you see, you get the Rex equation times phi is 0. Now, if the annihilator of phi is 0, then we get automatically the Rex equation. So that's what you have to do. So you have to make all these manipulations. And in the real case, you have a similar set. we have Fj psi is psi times Fj, and the partial derivative of the J flow on psi is this projection of calligraphic Fj psi for all. Now, so we will see what we have to do in the complex case, and then the real case goes in another analogous way. Now, what kind of manipulations we needed in 9 and 10? Then you have to be able to multiply phi from the left with elements from the pseudo difference operators. There are two examples there, and from the right with all basic matrices, and you should have an action of the partial sigma on that. That satisfies the Leibniz with respect to the left action of the pseudo difference operators, and of course this annihilator should be 0. Now, for the form of the elements in the module, you look first to the trivial solution. If you look at the trivial solution, then you get the equation 13. You get G sigma times phi 0 is phi 0 times G sigma. If phi 0 is a matrix, then it means that it has to commute with that. And remember, partial sigma was a substitute for derivation with respect to the flow parameter of G sigma. Now, then you easily see that phi 0 is the exponent of the sum of the T sigma. G sigma is a solution of the equation 13. T sigma is the flow parameter with respect to G sigma. Now, this is a decent matrix if you use some convergence conditions, and it commutes with the G sigma. Now, the module will consist now of formal perturbations of this trivial solution. You multiply formally on the left with elements from the pseudo difference operator, and then you get a collection O's SH of formal products of a part that is pseudo difference operator times this exponential factor. And you see, even if this phi 0 is a proper matrix, then this product you have to satisfy. So it's for the moment we keep the two factors separate, and the elements of SH are called oscillating matrices for the hierarchy. Now, how is the action of the from the left is elements from the pseudo difference operators? Now you simply shift the L1 inside this product, and that's all right. Multiplying from the right with G sigma, remember that phi 0 commuted with G sigma, so you shift in from the right. Now, and the partial sigma act on SH simply by pretending that the product is real, and you use Leibniz. Now, then you see that everything ends up again in the same module. So And this module is a free module over the pseudo difference operators. Is the generator phi 0. So you this annihilator is 0 as soon if you have an element phi that in this module that has the form phi hat times phi 0, this phi hat invertible. Then this annihilator business is okay. And if you look at the first equation of the linearization, the polygraphic G sigma times phi is phi G sigma. That you can directly translate. That means that phi hat is the dressing operator of G sigma. Now, if we look for the addressing operators that come from this group that we introduced before, polygraphic P minus R. Now, if phi hat is of this form, is phi hat in this group, then you phi you call a wave matrix for the matrices polygraphic G sigma if they satisfy the equations of the linearization. And we have made all the manipulations well defined, and then automatically what you get is G sigma are a solution of the hierarchy. And in the real case, then you only have to deal with Fj. Then in the same way, you see that the basis function psi 0 corresponding to the trivial solution is the exponent of the sum of the Tj Fj. And if you choose parameters in a good way, then this converts to well-defined Z-by-Z matrix. You define the module O AS in a similar way. The formal products of the real pseudo difference operators times psi 0. And all the actions are I spare you that it's simply just the same. Here we have the same and now we take psi hat from our deformation group polygraphic P smaller or equal than 0. Now, if this psi together with the polygraphic Fj satisfies the linearization equations, then we call psi wave matrix for these solutions. For the polygraphic Fj are a solution of the hierarchy. And those wave matrices are an analog for the present situation of the vector application functions for the KPR. Yeah, you have one piece that is decent, that's in the pseudo difference operator. We are going to look for wave matrices that satisfy the linearization equations. Now, the most difficult one is the second equation. That's the central one, everything. But you can prove something simpler. If suppose you have a file which phi hat into the group calligraphic P, there should be a minus R. So it is an element of the right form. If you have that, you can prove that its derivatives with respect to partial sigma is equal to an element from the skew hermitian subalgebra times phi, that should be a different phi, and then automatically it forms that it's the right element, the projection on G sigma. And it's the same, so you don't have to prove that it is this element what belongs to, that follows automatically. So you can simply only prove this simple property. And it's the same with for the derivative with respect to partial J of a good oscillating matrix psi. If you can prove that this AJ is anti-symmetric, then you're ready. So that's what we will do later on. Now, I come to the construction. And those wave matrices, those formal products don't occur in real life. So the only way to, or if you want to construct them, then you must use analysis to get proper products so that everything is well defined. Now, I work with the Hilbert space in HK, and in the real case, then the coefficients are in R, and in the complex case, they are in C. It's all elements of the all set by bounded operator is then multiplying from the left with the matrix B. Now, I know I'm going to make the commuting flows that occurred in the whole story that I told. That they are inside the exponential factors that I use. So I give them a convergent footing. Now, if you look at multiplication with G sigma, and that's an operator that has operator norm small or equal to 2, and the same holds for the FJ. Now, so how I choose the flow parameters, I take simply that the T6 sigma and the TJ are in L1. Yeah, so the sum of the absolute value of all the parameters here. And on this space you have this norm. Now then we have two analytic maps. The first you take the T sigma, and then you map it into the bounded operators, and that gives you a map from L1 sigma to the bounded operators on HC. And this, the other one is you said TJ. Yeah, here should be J's. It's, and that leads to a map from L1 of J to the bounded operators of HR. And we call the images of these maps by gamma sigma and gamma j. Now I worked all the time with a setting that was hanging in the air. I will be now concrete. I take for RR the C on infinity functions on L1, and then R consists of all C valued C on infinity functions on L1. The matrix is now of gamma sigma, T sigma is well defined, and also the coefficients of this matrix belong to R. And for the derivation, we choose partial derivative with respect to T sigma. And we do something similar for the real version. And then we take the CL infinity functions on the space L1J. Also here the matrix becomes well defined, and we choose all the partial J equal to partial derivative with respect to Tj. Now I need a group of I take the Hilbert-Smith operators on HK, and then what that are the bounded operators A, such that if you look at the matrix of A, then the matrix coefficients should be square summable. It's mapped onto itself by taking transpose or adjoint, and becomes a Hilbert space if you take the inner product of A and B equal to this sum. And now we take a group G2K. All elements of that are invertible and have the form identity plus Hilbert-Smith. It's a Hilbert Lie group with Lie algebra equal to the Hilbert-Smith operators. And the decompositions that we saw in the at the beginning of the talk, in the pseudo difference operators, they induce splittings of the Hilbert-Smith operators. So you have the Hilbert-Smith operators such that A star is minus A, and so on, such that the matrix of A is is a pseudo difference operator of degree 0, leading diagonal in R, and all other diagonals in C. And it's the same for and the second corresponds to all lower triangular matrices that have on the central diagonal only illustrable positive entities. Now, those two groups have no intersection, and if you look at the map from B minus times U2 to C2C, and simply multiplying B minus with U, then this map IC is injective, locally diffeomorphism, and bel theta has shown that it is even surjective. So this map IC is a diffeomorphism of the group, and that splits in two components, P minus and Q2. And so the inverse of IC is determines decomposition of the group G2C. And that's the Iwasawa decomposition. Now, if this product P minus times U is injected, if you multiply with P minus inverse times U, then this is also a diffeomorphism. And we use the inverse of this map, dus the inverse of I tilde C, that gives you for each G in this group G2C, there is an element P minus G that belongs to P minus and UG that belongs to U2, such that G is P minus G inverse times U. And these are used. The same we have in the new case, also the result of bel theta holds also. And I use again here also this twisted Iwasawa decomposition. Now I will give the construction in the complex case. The real one is goes the same. What we do? We take a G and the G2C and conjugate it with the flow group gamma sigma. Now then I get another element in G2C, and I apply the twisted Iwasawa decomposition. Then I get P minus E inverse times U T sigma. And both components depend in the C infinity way of this. Now, if you define phi by P minus J T sigma times gamma sigma T sigma on the matrix level, then this phi is in potentially is an oscillating matrix. For the, you have there the second one is phi 0, and you have an operator of the good form. So phi is a candidate wave matrix for the hierarchy, and all the products are well defined. Now, thanks to this proposition, I only have to show that this if I let partial sigma act on phi, that it is equal to skew hermitian operator. Now, if you differentiate, and let's here, we have two expressions for phi. First, the one with P minus and phi 0, and there you have this UG and G and again phi 0. So if I differentiate this one, now what you see, I get here downstairs. You see some expression that's oh no, sorry, in the middle. There you see times the phi dropped out, so I get a matrix S sigma, which belongs to the pseudo difference operators. So that I don't know. Now I look to the one with the UG factor, and what I see, I got this factor and that. Now that's U is a unitary matrix, and G sigma is so this right one is already in the skew hermitian operators. Now, for the first part, that holds also for if you differentiate this part with respect to the partial sigma, then you get that this matrix is also skew hermitian. So I get that he is skew hermitian and belongs to pseudo difference operators, so he is in this SHR subspace. And what we know, phi is a matrix for the hierarchy. We can simply, we can still say a little bit more. If you replace G by an element G times U, is U in the unitary group, then from this computation here, you see that the P minus factor remains the same, is equal to the P minus factor of G. So, and the conclusion is that G and GU gives the same solution of the hierarchy. Now, and that's formulated in this. You have an element from the group C2C. If you conjugate with this element P minus G, you get a solution of the hierarchy, and the solution doesn't change if you replace G by GU. And the symmetric space G2C modulo U2 determines the solution of the hierarchy. And in the new case, you get that the symmetric space of all elements from G2R modulo O2 modulo the orthogonal group determine the solutions of the. So in this case, you get in the case of KP, you got Gauss-Median. In the case of discrete KP, you get a flat variety, and in this case, you get a symmetric space. So if you choose the in a different algebra decomposition, then you will end up also with a different group of homogeneous space of solutions. So this was what I wanted to say.
Any questions? The classical examples of total lattice of the Gerard equation, do they fit the string? Because
Yes, examples of this in the infinite total chain is
exactly right. So this year is 50 years when these equations were discovered by Manakov and Lashkar, right? And after that, 50 years ago was spectral transform method, which linearizes equation. Then was a bunch of works, including Christian on finite gap solutions, solid solutions. It is known that some Tenderer equations can be, expressed in solution of this equation in Tenderer, etc. So lots of work in 50 years. I wonder what your approach is to this bunch of work. works? I mean, can you find new solutions or can you solve? So was, even as it was developed, so much work was done. I just want to see where your work is in, I mean, how it fits with my works in 50 years.
I worked before on this KP, this KP, and I saw a possibility to fit in that analytic framework from there to these equations, and we just started to see what can be done more. If we can, for instance, integration construction that fitted also in this manual picture. So we would like to find that here too.
Questions? Okay, no more questions. Let us think.